Hello everyone, welcome to today's webinar called the Noise Prediction of Moving Mechanisms Using Coupled MBD Acoustics Analysis. My name is Yijin Feng. I'm the Product Marketing Manager for Adams and EZ5 at MSC Software. Today, co-presenting with me, we have Dr. Diego Colpiello. He is the Product Marketing Manager for Actran. So in today's presentation, we are going to basically introduce a new technology that we developed recently to couple Adams with Actran. There are two different methods we can do that. We will talk about that later in the presentation. So let's briefly go through the agenda for today's webinar. So first we will give a background introduction as to why we developed that toolkit and what's the reason behind it. Then we will, to those who are not familiar with multi-body dynamics and acoustics or acoustic simulation, for example, if you have not used Adams or Actran before, we will spend about 5 to 10 minutes talking about those two solutions, briefly introducing that so you can get a general idea of what it does or how they can be used in different applications. After that, we will dive into the two different methodologies using which you can integrate Adams with Actran. So there are two different ways you can do that. We will talk about that in that workflow section. After the workflow section, we will talk about the differences between the two toolkits. So if you are, for example, in the NVH department, which one you should probably use, or if you are Adams user or if you are Actran user, which toolkit should you pick for your specific scenario? So we'll talk about that. And at the end, we will have two demos. One demo for each workflow, which means each toolkit. And the first demo will be conducted in Adams, and the second demo will be conducted in both Adams and Actran environment. Okay. First, why did we introduce this technology? The main motivation behind it is that it is generally very difficult for the engineers to predict the noises coming from a moving mechanism, like a transmission system, like a gearbox. The reason is that, first, there are really very complicated moving parts inside the system, and there are various ways in which those parts can interact with each other and cause varying contact forces and vibrations. And all those contact forces and vibrations can affect the noise that's coming out from the gearbox. That's the first thing. And the second reason is that it is also pretty tricky how you can understand what the dynamic performance is going to influence in the radiated, about the radiated noise that's coming from those products or mechanisms. So first, understanding the dynamic mechanism inside those systems, and secondly, understand how those dynamic performance can influence the noise behavior of the system. Those are the two big challenges for engineers out there. So that's why we want to introduce two different integrated technologies to couple those two solutions for different applications, for different fidelity level, and for different scenarios. And that is the main reason we introduced this technology. So next, let's take a look at what kind of application can you basically apply this technology to. So for the applications, some of the very typical applications that we can think of, or through talking to customers, are things like the powertrain and the transmission, how you can predict the noise coming out from the casing. Or if you want to study the gear moan noise or the gear rattle noise, you can also do that by making the gear pair flexible. and then you will be able to predict the noise directly coming out from the gear pair. A second application scenario we can think of is the vehicle NVH, the full vehicle NVH. For example, a vehicle driving on a rough road. So what is going to be the noise coming out from the exterior of the vehicle? The noise can be generated by the contact between the tire and the rough surface, or due to the different interactions in the suspension system or in the chassis. So basically what kind of noises will be generated outside from the vehicle. Other things can be applied, like the wind turbine, how, if the rotor is operating under different speed, how that can affect the driveline system in the wind turbine, the noise performance of the driveline system. Besides, you can also study things like the switch for the power window, so the noise coming out from the contact between the different switch parts, so how to predict that noise. Also the door latch mechanism, when you close the door or you open the door, how you will be able to accurately calculate or predict noise coming out from the different mechanisms that you put into those different products. And once you know how to predict those noise, then you can change your mechanisms to tune the noise into the way that you want. So basically, there's no restrictions as to like what is the application. So anyone who wants to evaluate noise coming from a moving mechanism can benefit from this workflow or technology. Okay, now first let's go through the multi-body dynamics. I will talk briefly through what is Adams and what it can do. Then I will pass the presenter to Diego. He will briefly talk about, introduce the Adams-Actran. Okay, so to those of you who are not familiar with multi-body dynamics, here are some of the reasons why engineers or CAE analysts out there are using Adams or are running analysis based on multi-body dynamic code. So first, it is very important to leverage the system-level analysis. So many problems come not only from the component interactions, but that can come from the interaction between different subsystems. For example, if you can observe and there's like a Moen noise from a braking mechanism, that Moen noise might not come from the braking system itself, but rather it can be the resonance effect between the braking system and the suspension system. So the operating frequency of the braking system might excite one of the natural frequency of one of the components or one of the subsystems in the suspension system, and that can cause some of the more complicated issue which cannot be observed by, like for example, FEA solution itself. So another reason is that we do provide very accurate dynamic loads for the FEA, as well as, like we will mention in this webinar, the acoustic simulation. So the Actran code here is also based on the FEA standard. So what we can do as one of the workflows is to provide a very accurate surface response as the boundary condition for the Actran to perform the subsequent acoustics analysis based on. And also you can do things like the optimization analysis, optimizing the geometric configuration, perform the vibration analysis, and also integrate Adams with some of the control systems out there to evaluate whether or not you can have a working or sophisticated control algorithm for things like the ABS or the the active suspension system. And of course, analyzing problems with moving part, you can have a much more efficient solution with the multi-body dynamics than you can do with the FEA. So just imagine running a full vehicle analysis using a finite element code, which will probably take you days or even weeks to do that. But with the multi-body dynamics, you can finish that analysis in a couple minutes. And also, if you want to add accuracy into the simulation, you can make some of the critical parts flexible. So you can also come into the deformation of certain critical parts. So you can perform the analysis with moving mechanisms, with accuracy, and also with high efficiency. Last but not least, you can perform various kind of DOE analysis or optimization analysis to study or to optimize your design configuration. So why Adams? Why not some of the other MBD code out there? So first, we provide a very robust and accurate implicit and explicit dynamic solver. It has been used by various industries for more than 20 years. It's a really trusted solver, and we keep upgrading that and keep making it more robust and faster. And secondly, we have a very reliable connection between Adams and other control logics out there. So we provide a very accurate and reliable control. Next, we provide a strong coupling between subsystem and the full vehicle simulation. For example, if you are a transmission designer, you can basically couple your analysis, the subsystem analysis, with your full vehicle analysis. And you can use the model you created in the transmission department and use it in the full vehicle scenario. Next, one of the other benefits is that we provide highly customized tools like Adams car or Adams machinery, which are designed for some of the common mechanical components like gears, bearings, chain, belts, and cables. And also for Adams car, we have a list of predefined vehicle event which is ready to go, so you can directly use the assembly we have embedded in the Adams car, customize your own vehicle, and then run different types of evaluation for different types of vehicle events. Last but not least, we have a very accurate and fast contact formulation, which is also unique in the MBD industry. So those are some of the reasons why you should pick Adams as your go-to MBD solution. And here are some of the customers out there who have been benefiting from using Adams for many years. So we have customers from automotive industry, aerospace industry, and general machinery industry. Overall, we have over 10,000 companies out there in the world which are using Adams to help with their R&D design, daily R&D design. And here is another slide which you can see is the common applications people use Adams for in the automotive industry. So different types of vehicle events like ride and handling or the safety events. You can also use Adams to study your powertrain, perform the durability analysis, or study how the driveline can affect your full vehicle performance, things like that. Okay, now I am going to pass the presenter to Diego. So Diego, let me know when you want to move to the next slide. Okay.
Thank you very much, Jun, and good morning, everybody, for this webinar. So we will start with we'll now discuss acoustic simulations, and specifically we'll see first of all why we need to study acoustics. The first consideration that we have to make is that first of all we have norms and standards that are becoming more and more restrictive, and this sometimes can become a dimensioning factor. Here on the right you can see an example of the 5 noise levels that are allowed during the decades the evolution of the pass-by noise levels allowed by norms, and as we see, we have a constant decrement of these levels. The second reason why we could need to study acoustic is comfort. Indeed, acoustic comfort is becoming a marketing argument today, and this is true for a car, for an aircraft, or as well for heavy machinery, for example. This means that we need to study acoustics, but then we need also to make acoustic simulation. Why this? Basically because prototypes are expensive and typically involve too late in the development cycle. So if we want to reduce the development cost of a certain product, definitely we need acoustic simulations to improve our product itself. Next slide, please. So if we do acoustic simulations, well, we have to consider two main design challenges that are related to two different aspects. The first thing to consider is the design challenge related to the noise source. This means that we need to address the acoustic performance of the noise source itself. So it means that if we make, for example, a simulation with Adams and we want to improve the acoustic performance of a product, for example, we can change the material or change the structure shape. But then we need to have a tool, a simulation tool, that allow us to address the acoustic performance of our product itself. But then, if we want to further improve our acoustic performance of the product, what we can do is to study the propagation mechanism and try to affect the propagation mechanism itself. How do we do that? Well, for example, we can add covers or try to redirect the noise towards area where it is less important. Or finally, we can also introduce insulation with porous materials. And for that, we will need a dedicated tool. Next slide, please. Here is just a few elements to consider why using Actran. Well, Actran, first of all, is efficient, then it's accurate and easy to use. It is efficient because it has dedicated features that allow to do massive simulations. So, for example, it has the adaptive meshing technique that will be the focus of the next acoustic webinar. Then it has in it some finite element algebraic solver advances or HPC breakthrough. By means of them, we can really solve massive models and go through parallel execution. And this means that we can really go to higher frequencies compared to 1 decade ago with classic FEM tools. Then Actran is an accurate solver because it is validated by FFT during the development of the code, but it is also validated versus experiments by our customers on their applications. And finally, it is an easy to use software because it has a dedicated user interface. It allows scripting capabilities for automatic pre- and post-processing. And finally, it is interfaced with FEA tools or MBD tools such as Adams, and that's why we are here today. Next slide, please. So what kind of outputs Actran generates for helping us in addressing the acoustic, any acoustic issue? Well, we start from maps or animation, for example, that help us to understand the physics in a certain problem. Then we will have frequency response function or spectrum at specific microphone locations. We will have waterfall diagrams. We will see one example during the demo. And we can understand the element contribution, meaning that if we have a certain simulation, a certain structure that is vibrating, we want to know each element, how each element contributes to the noise to our microphone location. Then we have also the acoustic directivity to understand better the directivity of the noise. And finally, also time domain pressure and sound files. Next slide, please. So Actran is widely used in a very wide range of applications. So for example, of course, transport and vehicles in aeronautics, aerospace, automotive, but also in machinery for factory, for example, industrial machinery or factory equipment, and finally also in consumer goods. So for example, loudspeaker, hearing aids, or even domestic appliances such as vacuum cleaners. Next slide. And this is just few examples of the customers that are currently using Actran for their own applications. So we have customers, of course, in automotive, aerospace, then also machinery and consumer goods, as well as others. That's all from my side, John. Thank you.
Okay, thank you very much, Diego. So now let's go through two of the workflows we have developed for this coupled analysis. First, we will go through a toolkit, which we call the Adams-Actran toolkit, with a coupled chain analysis. So what we mean by chain analysis is that we will get the results from one software and then import that result into another interface and perform the subsequent analysis. So here, let's take a look at the conventional method, how people usually perform those type of simulation with a moving mechanism. So first, they would use an MBD software to generate the dynamic loading. Then they will use some sort of FEA software to convert the dynamic loading results from the MBD software into the OP2 surface response result file, which is readable by the acoustic software. So in the conventional method, which is still prevailing, you can see we are leveraging 3 different interfaces in this entire workflow. So with this new toolkit that we have developed called the Adams-Actran toolkit, we are now enabling the user to directly connect Adams, which is the multi-body dynamic software, with Actran. So we're directly enabling the direct connection between those 2 software, which the toolkit basically what it will do is to convert the Adams results into the OP2 results, which is can be read into the Actran later directly in the Adams environment. So, and let's take a more detailed look at this particular workflow. So currently, if you have after you're done with an Adams simulation, what you can do is to set up the parameters in the toolkit, then run the toolkit. Then you will be able to convert the dynamic loading into the OP2 file. The OP2 file, which can be later used as the boundary condition in the Actran environment for it to perform a very accurate acoustic simulation. And this is how the toolkit looks like. We will later we will go into the software and take another look at this interface. So basically, what you have 2 different ways to convert the dynamic loading into the OP2 file. The first is using the Adams Flex technology, which is embedded in Adams environment. The second way is that you can do that by MSc-Nastran. So for those of you who are running a token system, or if you have MSc-Nastran, use MSc-Nastran as your FEA software. You can choose either way to convert the results. This is one of the examples that we will talk about later. So this is a transmission system, a gearbox, and the gearbox casing is a flexible body, which is generated by one of the FEA software. So any FEA software which can export the modal neutral file can be used to help creating this flexible body in Adams. And in this scenario, all the gears inside the gearbox are rigid. So what we are doing is basically we are running the Adams simulation, and then we are converting the dynamic loading on the surface of the gear casing. We're converting that dynamic loading into the surface response or the surface vibration, which is later read into Actran and perform the acoustic simulation. So this is the Adams simulation with the gear casing made flexible. you can actually see all the different contact forces between the gear pairs inside the gearbox. So all those forces are, so all the effect of those forces and vibrations are migrated or are reflected in the final OP2 file that we export into the Actran. So with this solution, you can really capture the effect of how the moving mechanism and varying forces can affect your noise performance. And the picture here is one of the sound pressure plot you can get from the Actran post-processing. And you can actually hear the noise. I don't know if it's loud enough to hear it here. Try to play that. So you can actually get the sound pressure results and as well as hearing the actual noise coming out from this mechanism in the simulation. Here's another example with the piston slap noise. So what we did here again is that we made the casing flexible and all those pistons are in contact with the casing. So since we are changing the speed and the rotational speed of the shaft, the noise of the piston is also changing with respect to the time. And in the subsequent Actran model, you can actually see the sound pressure from the frequency domain, which is some more advanced post-processing technology in the Adams interface. Again, I think you can also hear noise. So this is the noise of the actual piston slab that we simulated in the Actran environment. The second workflow or technology we want to introduce is a different approach. So we call it more highly integrated solution. So for this toolkit, what we basically did is that it is an automated interface that embeds Actran simulation into the Adams environment. So the main difference between this toolkit and the previous toolkit is that you can perform the acoustic analysis in the Adams environment, and you can get some preliminary acoustic results in the Adams post-processor. It is so the basic technology behind it is that when we are running the simulation using this toolkit, it automatically uses Adams-Actran to convert the Adams results into the OP2 file, into the results that can be that's readable by the Actran, and it is also leveraging the Actran solution. So it activates the Actran solver in the background. Everything is connected in the background. You don't need to worry about that. So once you click the button, after the calculation, you will get the acoustic results. So, and here are some of the examples which you can perform with this technology. First is the things like the wind turbine drivetrain analysis. You will be able to analyze, like if you have either a constant rotor speed or if you have a changing rotor speed, what is the acoustic excitation coming from the housing of this gearbox? You can also study things like the exterior acoustic of a chassis. So you will perform an Adams simulation where the vehicle is driving on like a rough road or a Belgian road in this case, and see what is the surface response of the exterior on top of the vehicle. Once you get that results, you can also study the acoustic. You can perform some of the noise prediction of the exterior frame of the vehicle. So you can study what is the noise coming out from the vehicle itself. And some of the differences between the two toolkits. First, the toolkit that we introduced, there are two different toolkits. The coupled chain analysis toolkit, which is the one on the right-hand side, is designed more for the acoustic engineers. So now the acoustic engineers can really get the accurate boundary condition from the multi-body dynamics software, and you don't need to and the process itself is much more convenient than the conventional method. So you can directly get the results and perform the acoustic analysis in the Actran environment. And of course, you need someone in your department who knows how to use Adams and perform those type of analysis and get you the ideal results you want. Compared to the chain analysis method, the highly integrated method is designed more for the Adams or NBD engineers. So with this technology, you can get the initial acoustic results without going back and forth between the Adams and Actran environments. So everything can be completed in the in Adams, either Adams View or Adams Car with Adams Post Processor, which I will show you later in the demo session. So, for example, if you are an Adams user out there, but you really want to study like what is the noise that's going to coming out from this particular mechanism that I just recently designed. So you can really do everything in one interface, which is the Adams interface. And if the noise performance or the acoustic pressure is not ideal, you can change your design and study if the noise performance is improved or not. So some of the benefits is like I mentioned before with this highly integrated solution. With the Japanese toolkit, which is the coupled chain analysis, one of the benefits is that MSc Nastran is not a prerequisite. So if you are not using MSc Nastran as your FEA solution, you can choose any of the other major FEA software as long as you can create the model neutral file using those FEA codes. Of course, it will be very beneficial to the Actran users because you can perform all the advanced post-processing in the Actran interface. So for a dedicated acoustic engineer, this coupled chain analysis might be more suitable for your situation. So the prerequisites for the two technologies. For the coupled chain analysis, you need Adams, you need Actran, you need any kind of mainstream FEA software which can help which can generate the model neutral file that can be used in the Adams to create the flexible body. For the highly integrated solution, currently what you need is that you need Adams, you need Actran. You also would need to have MSc Nastran solution 112 and solution 103. That is the current prerequisite for the highly integrated solution. So if your company is running on the token system, I would say this highly integrated solution is a more approachable solution to you. And we are also working on a updated version of this toolkit, which will allow you to use other FEA software to do the analysis here. So, but currently, this highly integrated solution, in order for you to work on that, you need to have Adams-Actran and MSc Nastran. Okay, so now those are some of the differences of the two different toolkits that we mentioned before. Now let's go through two demos. So we will go to the Adams environment and the Actran environment so you can see what those toolkits actually looks like in the Adams or Actran interfaces. The first demo is so there's a flexible gearbox housing and there are two spheres that's impacting the gear casing in this case. And the second demo would be the gearbox with several gear pairs inside the mechanism, which is the example you saw before. And we will perform the acoustic analysis based on the chain, the coupled chain analysis toolkit that we mentioned before. So first, let's take a look at the highly integrated solution, which is the this example. So, so for those of you who are not familiar with Adams, so this is the Adams interface. When there are different ribbon tabs here, and the toolkit is actually working as one of the plugins you have in the you can install in the Adams environment. And the toolkit is called the Adams-Actran here. So this is a so after you're done with the Adams simulation, for example, I can show you the. So some of the you can see the animation here is the Adams simulation with the sphere impacting the surface of the gearbox casing. And as you can see, the casing itself is a flexible part. So now, after I'm done with the Adams simulation, I would click this button and choose Actran analysis. Then I will pick the flexible body for this particular example. And there are some options here where you can, for example, show the acoustic mesh dimension. So you can see here, this is an area for the acoustic area for the noise analysis prediction, which Diego will introduce later in the Actran environment. And here are some of the microphones you can place around that gearbox, basically. Some of the more advanced setup, so you can choose what kind of output you want from this particular simulation. The environment, which means the speed of sound and the fluid density. You can define how large you want this acoustic sphere to be, and also some of the analysis parameters you can set up for this analysis, for this simulation. After you click apply, everything will be calculated in the background. So when you're done with the simulation, you will go to the Adams post-processor environment. And here you can see there's a button called the Adams-Actran, special post-processing. So you can choose to play the sound, which we have a WAV file generated for this simulation. You can also import the results. So you can choose the flexible body you want, and then you can import the results file, which is the A2AC file that is automatically generated after the simulation. So after you import the results, here is what you can get. This is a waterfall diagram, basically for the acoustic pressure on different microphones. So we have 40 different microphones placed around this mechanism. So you can study the acoustic pressure from the time domain on each of those microphones. So you can choose, different angles for this waterfall diagram, and get some of the other plots like the acoustic pressure or the average acoustic pressure on the specific microphone. So those are the results you can get, as well as the WAV file, which you can play the noise coming predicted from the simulation about this mechanism. So this is what, in brief, what the highly integrated workflow looks like. The second demo, we will take a look at the coupled chain analysis, which is the model is, as you can see, is illustrated on the screen here. So now let's take a look at the second toolkit, which will enable you to export the results from Adams into the OP2 file, which is later read into the Actran environment as the boundary condition. In here, you can choose different methods. You can choose to convert the results either using Adams Flex, or you can choose to convert it using MSc Nastran. So here you will pick the things like the flexible body. In this case, it's the flexible casing. You can choose the output type as the acceleration, velocity, or displacement. The modal neutral file, you will define that. The result file name. This is the results file you get after you're done with the Adams simulation, basically. And the output file name, you will need to create a text file in the working directory, and then choose this text file when you when you set up this this toolkit. There are some more advanced capabilities. For example, there are a median filter, which will cut out some of the noises from the simulation. And also there's a method called the mapping to coupling surface, which is basically so that you will have mesh on your flexible part, and later you will have mesh on the Actran model of this gearbox. So you would basically need to map the mesh from the flexible part in Adams with the mesh of the Actran environment, so you can map the results on different nodes into the Actran environment. And I think Diego will also talk about that later in the acoustic simulation. So that is all you want to know about this toolkit, and everything is embedded in the Adams environment, like I mentioned before. So after I'm done with that setup, I will click OK, and when the simulation is completed, an OP2 file will be generated, which will be given to an acoustic engineer, which in this case is Diego. So now I'm going to pass the stop sharing and then pass the presenter to Diego.
Okay, thank you, Jun. I will share my screen.
Okay.
Okay, so I think you can see my screen. So this is the Actran environment. So I will first of all speak about the analysis setup that is required by the so-called Japan toolkit. As Jun already illustrated, we start from the results coming from Adams, that are the vibration levels at the cover of our gearbox. So basically we start from a boundary condition that in Actran is known as BC mesh. Basically in the BC mesh we will select the mesh coming from Adams that is supporting the results in terms of OP2 files, and we will select the related OP2 files and the type of boundary condition. Now the mesh coming from Adams is different from the mesh coming required by Actran, because these are two different techniques, and so we have two different meshing requirements. This means that the results coming from Adams will need to be projected on the acoustic mesh. So basically we have in the BC mesh, BC_mesh.pdf that we see here, the mesh coming from Adams, and that will be projected on the coupling surface, that is the surface, the 2D surface for Actran. And the projection of these of the results are basically guided by the tolerance that is selected here. Once we have the vibration levels, set up the vibration level for the cover, what we can do is make the acoustic radiation in the near field thanks to the acoustic component, the so-called acoustic component, where we specify that outside our gearbox we have air. But then, after having the near field propagation, we definitely need to make the far field propagation, and this in Actran is done through the infinite acoustics, that are surface elements that are placed on top of this sphere. And by means of these elements, we will have the results on the microphones that are placed in the far field. This is a time domain analysis that is available in Actran 15 and can be run so with the parameters already set up also in Adams, meaning that in this case we have a simulation that is starting at 0 seconds and goes up to 5 seconds. Once we run this analysis, we will have two results. One is a map with the field, and I can display an example of this map. I have already loaded the mesh carrying the map. I need then to display the results. Okay, so this is the acoustic pressure on the outer surface. To see what's going on inside, we can apply a cut plane or even two, and then display the acoustic map. This is specifically the pressure, the acoustic pressure at 1.6 seconds. But then we need to analyze better the noise, and what we can do, we can basically take the output file generated by Actran at different points and in the time domain. And what we do, we display in the PLT viewer the evolution in time of the acoustic pressure for one or two or as many points that we want. From this, we can generate the audio file that we can do live and basically play it. So we generate it. And hopefully you have listened to the file. Then we can do some more advanced post-processing. We can export this file and perform a DFT of this signal and display basically this type of chart where we have in the bottom the frequency, whereas in the y-axis we have the RPM of our gearbox, and here we have the SPL for the point for the microphone, the virtual microphone that we have selected. And typically in this application what we see is that we see certain lines corresponding to different orders of our gearbox. In this case we see that this line, that is the order 25, around this frequency range increase, we have an increase of the SPL, most likely because within this band we have specific structural modes that are more excited. Now what we can do, basically we might be interested for this microphone to know what is the frequency spectrum at a given RPM. So let's make an example at around 1500 RPMs. We might need the spectrum, and what we can do, we just right click and get the spectrum in this the spectrum background in this window. Another possibility is that we need this, the noise content, the SPL, along this curve. This is of importance for gear noise, and what we can do is basically take perform an order analysis. So we know that that one is the order number 25, and what we have is that we have along this line we have the SPL as function of the RPMs. And so basically these are the types of post-processing that you can do for this kind of application. From my side, John, it's fine.
Okay, thank you, Diego, for your demonstration. So that will be all the contents we want to present here. So if you have any questions, please type the question down in the Q&A window. We will try to have them answered.